To understand where we came from, we must first understand where our components originated. And to do that, we must venture to one of the most extreme and violent objects in the cosmos. This is a story written in the heart of collapsing stars. A story that begins not with life, but with a ghostly particle buried in the heart of every atom. Consider the humble neutron. Within the nucleus of an atom, it plays a crucial stabilizing role. Protons, each with a positive charge, desperately repel one another due to the overwhelming force of electrostatic repulsion. Left to their own devices, a nucleus with more than one proton could never form. But the neutron, being neutral, introduces the strong nuclear force without adding that destructive positive charge. It acts as a nuclear glue, a mediator that allows the strong force to bind the nucleus together against the proton's mutual desire to fly apart.
The repulsive electromagnetic force between two protons in a nucleus is around 23 newtons to 24 newtons, which is around 2 kilograms at this typical separation of 10 to the minus 15th meters. Imagine a proton-size ant lifting 2-kilogram dumbbell. However, this repulsive force is overcome by neutrons in a nucleus as even stronger, at a typical separation of about 1 femtometer, 10 to the minus 15th meters. The attractive force is approximately 25,000 newtons. That's around 225 kilograms, which is approximately 130 times stronger than electromagnetism. Now, imagine a proton-size ant holding 225 kilograms barbell at nuclear distances to overcome the forces between two protons in a nucleus. Small atoms are stable because the strong force dominates, but as a nucleus grows heavier, it packs in more protons. Their collective repulsion overwhelms the strong force's short-range grip. To regain stability, the strained nucleus must shed energy and mass, which it does through the transformative process of radioactive decay. For example, the water molecule is small and stable, but a uranium molecule is very heavy and cannot hold itself, and it loses its weight by the process of radioactive decay. Neutron is a fermion. It obeys the Pauli-exclusion principle, a fundamental rule of quantum mechanics that states that no two identical fermions can occupy the same quantum state simultaneously. Think of it as the universe's ultimate rule against overcrowding. In a nucleus, this principle means you can't simply pack neutrons and protons in anywhere you like. They must occupy distinct energy levels. This has profound consequences for the stability of an atom. If you have too many protons, electrostatic repulsion dominates, tearing the nucleus apart. But if you have too many neutrons, you are forcing these fermions into higher and higher energy states to satisfy the Pauli principle. This, too, makes the nucleus unstable. There is a delicate, golden balance for every element. But what if we created an environment where we didn't rely on the strong nuclear force to hold individual nuclei together? What if we stripped away the atomic structure entirely and packed so many neutrons into a single, immense object at nuclear density that gravity itself finally became strong enough to take over? This seems counterintuitive. Gravity is, by a staggering margin, the weakest of the four fundamental forces. The electromagnetic force that makes a simple refrigerator magnet stick to your door is over 1 billion times stronger than the gravitational attraction between the same magnet and the Earth. To overcome the nuclear forces and the Pauli exclusion principle, you need a gravitational field of unimaginable strength. For that, you need an almost unimaginable amount of mass. And now, if you can manage to put all these neutrons in one place, then the gravity will take over and a neutron star will born. This is how neutron stars emerge in our cosmic universe. Our cosmic journey starts with the Big Bang, which provided the universe with the two simplest elements, hydrogen and helium. Under the relentless pull of gravity, these primordial clouds coalesced into the first stars and galaxies. Within the furnaces of these stars, nuclear fusion began to forge heavier elements, up to iron. But iron is a dead end. Fusing it consumes energy instead of releasing it. The star's energy production grinds to a halt, and the balance that has supported it against its own gravity for millions of years is broken. The core collapses catastrophically. In a star between about 8 and 20 to 25 solar masses, this collapse is so violent that it forces electrons and protons together to form neutrons. In a process so immense, it creates a neutrino burst that blows the star's outer layers into space in a supernova explosion. What remains is a city-sized object of almost pure neutrons, a neutron star. Our own sun, at a mere 1 solar mass, does not have the gravitational might to trigger this collapse. It will end its life as a white dwarf. But for more massive progenitors, the story continues. If the collapsing core is between about 1.4 and 2 to 3 solar masses, it forms a neutron star. If the remnant core is more than approximately 2 to 3 solar masses, not even the degenerate pressure of neutrons, the final stand of the Pauli principle, can hold back gravity, and the collapse continues into a black hole. The result of this stellar alchemy is an object of almost incomprehensible density. If our Sun, which is 1.3 million times the volume of Earth, were to be crushed into a neutron star, its entire mass would be compacted into a sphere no larger than a city, roughly 20 kilometers across, about the size of Manhattan in New York City. The density is so extreme that a single teaspoon of neutron star material would weigh billions of tons on Earth, a mass equivalent to a mountain held in the palm of your hand. But the story does not end with the formation of this incredible object. A neutron star is a cosmic crucible. During the supernova explosion that gives it birth, and in the chaotic mergers of neutron stars, conditions become so extreme that rapid neutron capture, or the R process, occurs. This process bombards atomic nuclei with a dense neutron flux, allowing them to build up into the heaviest elements in the periodic table. The gold in your jewelry, the platinum in a catalytic converter, the uranium in nuclear reactors, and the iodine in your body. These are not forged in the quiet fires of living stars, but in the violent, neutron-rich maelstroms of stellar death and collision. We are, all of us, children of the stars, but not just any stars. The iron in your blood that carries oxygen was born in the last breaths of a massive star before it went supernova. The very elements that allow for rocky planets like Earth, for complex chemistry, and ultimately for life itself, were seeded across the galaxy by these cosmic explosions and collisions. A neutron star is not just a relic of a dead sun. It is a creator, a distributor of the fundamental building blocks of worlds. So, when you look up at the night sky, remember that you are not just a passive observer. You are a collection of atoms that have journeyed for billions of years. You are made of stardust, yes, but more specifically, you are made of the ashes of stellar explosions and the precious, heavy elements forged in the hearts of neutron stars. The universe began with hydrogen and helium. Everything else, everything that makes the world we know, including you and me, was delivered by the life and death of stars, with the neutron star playing one of the most pivotal roles in this grand cosmic cycle of creation and destruction. What do you guys think? Let me know in the comments. And as always, don't forget to like and subscribe to Brainwave. Until the next time, take care.